Hello and welcome to this class of spectroscopy. This is my third lecture of the unit Introduction to Molecular Spectroscopy. In this lecture, we are going to solve some numerical problems based on Beer-Lambert's law and Heisenberg energy uncertainty relation. We will also discuss the basic elements of practical spectroscopy and how to represent a spectra. So let us start the class. In our previous classes, we have derived the Beer-Lambert's law, and it is given by the equation A equal to epsilon Cx, where A is the absorbance or optical density and is given by log of I0 by I. Here T is a term which is given by I by I0 and it is called the transmittance. Epsilon is the molar absorption coefficient or molar extinction coefficient. C is the concentration of the solution and X is the path length of the sample. We have also derived another relationship between the absorbance and the percentage transmittance, and it is given by A equal to 2 minus log of percentage T. Okay, so using this relationship we can solve some numerical problems. Another important relation, which is the Heisenberg energy uncertainty principle, and it is given by delta E into delta T is greater than or is equal to H by 2 pi, where delta E is the uncertainty in the energy and delta T is the uncertainty in the lifetime. This equation can also be written as delta E into delta T is greater than or equal to H cut, where H cut is equal to H by 2 pi. On rearranging the equation, we can write H into delta nu into delta T is approximately equal to H by 2 pi, where delta nu is the uncertainty in the frequency. From this equation, we can write delta nu is equal to H by 2 pi H into delta T, or delta nu is approximately equal to 1 by 2 pi into delta T. Okay. Now let us solve the first numerical problem. The question is state the Beer-Lambert's law. The transmittance of an aqueous solution of potassium permanganate at a certain wavelength is 1%, that is 0.01, for a 10 to the power minus 3 molar solution in a 1 centimeter cell. What is the absorbance and the molar absorption coefficient of KMnO4? So first part we already discussed about Beer-Lambert's law. We are going to solve the second part. So let us see how to solve it. We know that T is equal to I by I0 and it is given 0.01. So inverting this equation, we can write I0 by I is equal to 1 by 0.01, which is equal to 100. Now taking logarithm on both sides, we get log of I0 by I is equal to log of 10 square, and log of I0 by I it is given by A. So this implies we can write A is equal to 2 log of 10, which gives you the value of A equal to 2. That means absorbance is equal to 2. Now again we know that A is equal to epsilon into C into X. So from which we can write epsilon is equal to A by Cx. Substituting the value of A, C and X, we get epsilon equal to 2 divided by 10 to the power minus 3 mole per liter into 1 centimeter, which gives you 2 into 10 to the power 3 liter mole inverse centimeters. Then if we convert centimeter into meter inverse, then we will get 2 into 10 to the power 5 liter per mole per meter, which is the value of the molar extinction coefficient, right? Now here is another problem which was set in CSIR UGC NET examination. The problem is, on passing monochromatic light through a 0.04 molar solution in a cell of 1 centimeter path length, the intensity of the transmitted light was reduced to 50%. calculate the molar extinction coefficient of the solute in the solution given the value of log 2 equal to 0.301, and the options are 0.75 liter mole inverse per centimeter inverse, 75 liter mole inverse centimeter inverse, 750 liter mole inverse centimeter inverse, and 7.5 liter mole inverse centimeter inverse. Now let us solve this problem. So here we will use the relationship A is equal to 2 minus log of percentage T, and substituting the value of percentage T, we get A is equal to 2 minus log of 50, since the transmittance value is 50%. So therefore A is equal to 2 minus log of 50, we can write it is 100 by 2, and which will become A is equal to 2 minus log of 10 square minus log 2. So this implies A is equal to 2 minus 2 log 10
it
plus
will be minus
0.301. Okay, and A is equal to 2 minus within bracket 2 minus 0.301, and simplifying it, we will get the value of A is equal to 0.301. Now again we know A is equal to epsilon Cx, so substituting the value of A, C and X in this equation, we get 0.301 equal to epsilon into 0.04, which is the value of the concentration, into 1, from which we get epsilon is equal to 0.301 divided by 0.04, and on simplifying it, we get epsilon is equal to 7.525 liter mole inverse centimeter inverse. So therefore the option D is the right answer. Next we have another similar type of problem which was also asked in CSIR UGC NET examination. The question is, using cuvettes of 0.5 centimeter path length, a 10 to the power minus 4 molar solution of a chromophore shows 50% transmittance at a certain wavelength. The molar extinction coefficient of the chromophore at this wavelength is given, the options are given, and the value of log 2 is given 0.301. The options are 1500 meter inverse centimeter molar inverse centimeter inverse, 3010, 5000 and 6020. So just like the previous one, in this problem also we will use the relationship A is equal to 2 minus log of percentage T to determine the value of the absorbance A, and since the value is value of percentage transmittance is 50%, so we can calculate A is equal to 0.301. okay. So again, using the relation epsilon A equal to absorbance A is equal to epsilon Cx, substituting the value of A, concentration and the path length x, we get 0.301 is equal to epsilon into 10 to the power minus 4 into 0.5. This implies epsilon is equal to 0.301 divided by 0.5 into 10 to the power minus 4. This implies epsilon is equal to 0.301 divided by 0.5 into 10 to the power 4, and it is equal to 0.602 into 10 to the power 4 molar inverse centimeter inverse, and on simplifying it, we get epsilon is equal to 6020 molar inverse centimeter and inverse. So that means the option D is the right answer. Okay. Now the next problem, the question is, a particular molecule is known to undergo spectroscopic transition between the ground state and the two excited states A and B, its lifetime in A being about 10 seconds and in B about 0.1 second. calculate the approximate uncertainty in the excited state and energy level and the width of the associated spectral lines in hertz. Okay, so let us solve this problem. We know that according to Heisenberg's energy uncertainty relationship, del E into del T is equal to h by 2 pi. So from which we can write del E is equal to h by 2 pi into del T. So substituting the value of h and delta T and pi, we get delta E equal to 6.626 into 10 to the power minus 34 divided by 2 into 3.14 into 10, and simplifying it, we get delta E equal to 0.1 into 10 to the power minus 34 joule, or approximately it is del E is equal to 10 to the power minus 34 joule. Again we know that del E is equal to h into del nu, from which we can write del nu equal to del E by h. So substituting the value of del E and h, we get the value of del nu is equal to 0.015 hertz, which is the width of the associated spectral line. Okay, so these are very simple problems you can easily solve. Now the next problem, a certain transition involves an energy change of 4.005 into 10 to the power minus 22 joule per molecule. If there are 1000 molecules in the ground state, what is the approximate equilibrium population of the excited state at temperatures of 29 Kelvin, 290 Kelvin and 2900 Kelvin? And what would be the your answer have been if the energy change were 10 times greater? So I am giving you this problem as a homework, so you can use this relationship n upper by n lower is equal to exponential del E by kt, which is called the Boltzmann distribution law. So using this equation you can easily solve this problem. So you try to solve such type of problems from different books, and if you have any doubt or any difficult problem, then send it to me. Now next is basic elements of practical spectroscopy. So in various types of spectroscopic studies, in order to generate a spectra, we need a device which is called the spectrometer. The spectrometers used in various regions of the spectrum differ widely from each other in construction. We will discuss the construction and working principle of each kind of spectrometers in due course of time, but probably for the time being it will be helpful for you to know the basic features which are common in all types of spectrometer. So generally a spectrometer has the following components: light source, modulator, sample holder, analyzer, detector, recorder and output device. So these are some basic components of any kind of spectrometer. It may vary from spectrometer to spectrometer. Now let us consider a general emission spectrometer as shown in the figure. So in this type of typical emission spectrometer, the excitation is actually initiated by often using electromagnetic radiation from a source. A modulator is placed between the source of excitation and the sample, which allows radiations having required frequency or wavelength to strike the sample. After excitation, the emitted radiation is analyzed by the analyzer, which ensures that only emissions recorded from the sample arises directly from excitation and any other spontaneous emissions is ignored. The detector then processes the radiation collected from the analyzer and send the data to the recorder or computer. some sophisticated softwares are installed in the computer, and the spectra is generated with or using the softwares. Okay, so this is the basic working principle of a general spectrometer. Now, to understand how a spectra is generated and how it is represented, let us consider a grating spectrometer. The schematic diagram of such a spectrometer is shown in the figure. This type of spectrometer is suitable for use in UV visible and infrared regions of the spectrum, and this kind of spectrometer are also known as dispersive spectrometer, since the grating disperses the radiation into frequency components. As shown in the figure, radiation from a source is passed through narrow slits S1 and S2. In between S1 and S2, a rotatable grating is placed, and with the help of mirror M1, a parallel beam of radiation is reflected onto the grating. When the grating is rotated, a succession of frequencies is swept across the mirror M2, from which it is focused to the slit S2. From S2, the radiation falls on M3 and then strikes the sample. After that, the emitted radiation is passed to the amplifier and then to the recorder, which then generates the spectra. Now, let us consider what happens when a spectrum is recorded. When the radiation strikes the sample, having just two energy levels, say E1 and E2, the detector output will show a sudden fall at frequency given by nu equal to E2 minus E1 by H. Since some of this frequency will be absorbed by the sample and will no longer reach the detector, so the resulting trace on the chart paper is illustrated as shown in figure A, where we can see on the left of the detector output with 100% at the bottom, and on the right hand side the percentage of the energy absorbed by the sample is shown. That means the spectrum has been scanned between the beginning and the ending frequencies, and such a picture is referred to as the spectrum in the frequency domain. The figure B illustrates a more typical spectrum, and in this spectrum many small peaks are arising from randomly generated electrical signals on the detector and the amplifier, which are collectively referred to as noise on the spectrum. Now let us see that the representation of spectra in electron spin resonance or electron paramagnetic resonance spectroscopy. So in ESR or EPR spectroscopy, relatively broad lines are observed in the microwave region. Such spectra are recorded in the derivative mode. So the derivative of a curve is simply its slope at a given point in calculus notation, and the derivative of the spectral trace is given by dA by d nu, where A is the energy absorbed or emitted. Okay, the derivative of the record is thus the plot of the slope dA by d nu against nu. So as shown in the figure, this is the broad absorption band, and this one is the spectrum in the derivative mode. Okay, so there are some advantages of recording a spectra in the derivative mode. So basically two advantages are there, which are that a derivative spectra indicates more precisely the center of the broad absorption peak, and secondly, the width of the peak is often more accurately measured from the derivative curve. So due to these two advantages, the ESR or EPR spectroscopy, the spectra are recorded in the derivative mode. Okay, so let us stop here. This is all about today. Thank you very much for your patience. See you next week. It's bye bye.